All right, so the last part of Chapter 8, I think, is one of the most challenging parts of Chapter 8, but I think we've built up enough practice where it will be fairly intuitive. And this is when we're comparing a reaction and trying to determine whether or not it'll be an SN1 reaction, SN2 reaction, or an E2 or E1 reaction, or some combination of the above. And the easiest way to do this is to kind of break it down into some simple rules. And the first thing I typically look at is the nucleophile or the base. So for example, in this first flowchart, let's say we've got something that's a good nucleophile, but it's not basic. Does anybody have some examples of that? Like something that could act as a nucleophile but is a really crummy base?
Sodium hydride.
Which one? Sodium hydride is a really good base, but not a good nucleophile. So you're on the right track, just flipped. What's that? Chloride. So something like a halogen. So we could have chloride, bromide, iodide. These are all conjugate bases of really strong acids. So they're not going to be a good base, but they're still nucleophilic. They've got that charge. Another one that's really popular is to have some sort of thiol or thiolate. So you could have SH or SR, and that R in this case is going to be some sort of carbon chain. These are all really good nucleophiles, but not very good bases. Why is SH not a good base, but OH is?
Hydrogen bonding to OH.
So hydrogen bonding, what's the other trend? The size, right? Sulfur is really big, it's stable with a negative charge, where OH is not. That means OH is going to be a lot more basic. Okay, so if we look at this, let's break it down. We've got methyl substrates, we've got primary substrates, we've got secondary substrates, and we've got tertiary substrates. So if we've got a good nucleophile, are we going to do any elimination chemistry if it's not basic? No, absolutely not. We're kind of stuck with SN1 or SN2. So if we're looking at methyl groups and primary groups as our substrate, are these going to do SN1 or SN2? Yeah, SN2 only. And we said if you've got a tertiary carbon, that backside's super duper blocked, can't do SN2, sterics are getting in the way. So this will only do SN1 reactions. Secondary carbons, we said, are kind of the wild card. They can do either. Oop. However, I'm going to do a little asterisk down here. And what can we do to favor SN2 over SN1 with the secondary electrophile? Yeah, change the solvent, right? So if we really, really want to destabilize that nucleophile and push it into an SN2 reaction, we want to use a different solvent. What solvent might work well? DMSO, something polar aprotic. If we're looking at the methyl groups or primary electrophiles, solvent really doesn't matter as much because you're kind of stuck doing SN2 regardless. So you can actually get away with using a polar protic solvents simply because you're stuck with one option only. Okay, so that's what we typically do when we're looking at a good nucleophile that's not basic. Now let's do the flip. What if we've got a good base that's not nucleophilic? Does anybody have some examples of good bases that are not good nucleophiles?
Sodium hydride.
Yeah, sodium hydride. Yeah, DBN, the alphabet soup. DBN, and there was a relative of that was DBU. Both of these are really nice non-nucleophilic bases. We said sodium hydride's not nucleophilic because it's not soluble. And then DBN and DBU are those big bicyclic ring systems that really are crummy nucleophiles, but they're resonance stabilized as a conjugate acid. So they're great bases. Okay, so if we've got a good base that's not nucleophilic, again, we're going to be doing some elimination reactions, but we won't do any substitution reactions. Oop, so we'll do the same sort of chart again. Can we do any elimination reactions on a methyl substrate? No, what's the problem?
No beta protons.
Yeah, no beta protons on a methyl group, so we could say not possible. No beta protons. With primary carbons, if we've got a good base that's not nucleophilic, will it do E1 or E2? E2? So good bases really like to do E2. What about secondary carbons?
They're all E2.
They're all E2, right? Good bases always do E2 reactions. It doesn't matter if it's primary, secondary, or tertiary. Sterics don't matter with elimination reactions, at least not in terms of the reaction being able to occur. So all of these will do E2. If we think about these, which one's going to be the fastest reaction? The one with the tertiary electrophile, secondary electrophile, or primary? Tertiary. So we'd say faster rate if substrate is more substituted. So that's a common trend with E2 reactions. Now we get into the tricky situation. What happens if we've got something that's a good nucleophile and a good base? It's not as simple anymore. So we'll write good base that is also nucleophilic. All right, so let's take a look at this. But before we do, actually, let's go back up and look at this top one. We said SN2 reactions occur with methyl and primary. SN1 occurs with tertiary. We've got to remember the trends, too. So if we look at this one, the fastest SN2 reactions will be which ones? Yeah, the methyl ones. So the trends are a little bit different for SN2 versus E2. With SN2, we said it's faster based on sterics. We said that SN2 is actually faster the more substituted it is based on hyperconjugation. So we've got two competing trends, which helps us a lot when we're dealing with something that's both a base and a nucleophile. So let's go ahead and come up with some examples of compounds that are both good bases and good nucleophiles. What's something that could be a good base but also a good nucleophile?
Hydroxide.
Hydroxide, so sodium hydroxide. Specifically, it's the OH minus. The sodium is just a spectator ion, right? Alternatively, we could have some sort of R group hanging off. However, I'm going to put a little asterisk. Why do you think I'm putting an asterisk on there?
Depending on how large the R group is.
Yeah, it depends on how big that R group is. If it's really bulky, that means that it's a good base but a poor nucleophile. If R is bulky, then it is only a base. It's going to be a pretty crummy nucleophile if it's really bulky. There are a handful of other strong bases that are also strong nucleophiles, but in general, these are going to be the ones that you see most commonly, the alcohols or the alkoxides, or sorry, the hydroxides or the alkoxides. So we've got methyl, we've got primary, we've got secondary, and we've got tertiary. All right, we know in general, this side favors SN2. And we know that on this side, E2 is faster. Right? We said we've got these competing trends, which really is quite helpful. So if we think about our methyl or our primary groups, do you think they're going to do any SN1 chemistry? Probably not if it's a strong nucleophile or strong base. But they can do SN2 chemistry, right? So in this case, methyl groups can only do SN2. And that's partially because it only has the possibility to do SN2. It doesn't have any beta protons. It can't have any other option. Primary carbons will do primarily SN2. Let me move this over a little bit. Once we go to secondary carbons, we know SN2 is a little less likely because that backside attack is going to be pretty darn blocked. So we'll do SN2 minor. And then tertiary carbons we know can't do any SN2, so they just simply won't exist. So we'll write no SN2. Okay, so we're kind of seeing this trend where methyl only does SN2, primary is major, secondary is minor, and then tertiary we get none at all. With E2, the trends are reversed, where we get only E2 with tertiary carbons. And then with secondary carbons, E2 is going to be major. With primary carbons, what do you guys think? Minor. Pretty simple trend. And then with the methyl one, we said no E2 is possible. One thing I will say is every year I get students that just try to brute force memorize their way through these flowcharts. That's a really horrible strategy. Not only is it really overwhelming, but you forget it immediately after winter break and you come into second term not remembering. So if you can, try to memorize these trends. Trends are important to memorize, but not the absolute flowchart. Don't rely on that. Try to test yourself on trends. Okay, and there are some weird exceptions, typically involving primary groups that have sterically blocking groups further away. Those can favor E2 a little bit over SN2, but these are good general guidelines. Okay, so now we've got our last class of molecules. These are things that are weak nucleophiles. That are also weak bases. And what are some examples of things that are really weak nucleophiles that typically don't have a charge? Water. Water can act as a weak base too. We know that from Gen Chem.
Acetate.
Acetate could be. So let's do this. It's not a super strong base. It can sometimes do SN2 chemistry, so we've got to be careful with this. I'll just put this down as an asterisk where this works under some circumstances. Primarily, if you've got a primary carbon, it can do SN2 chemistry, so we've got to watch out for that. What's another example? Alcohols. Any others? I'd say maybe some thiols, things like that, but in general, these are going to be neutral molecules. So in general, these are neutral molecules with a lone pair, or lone pairs for that matter. All right, so let's come up with that same sort of list again. We've got methyl, we've got primary, we've got secondary, and we've got tertiary. All right, are we going to do any reactions on methyl carbons if we've got a weak nucleophile or weak base? Probably not SN2 because we don't have enough oomph in our nucleophile, right? And it's probably not going to be SN1 because that would give you a primary or a methyl carbocation. So really we can say not practical. What about primary carbons? Usually not practical with primary carbons. So I'll just write these as usually not practical. However, we know with tertiary carbons we definitely can do chemistry off of them because they go through relatively stable carbocations. So typically with tertiary electrophiles you get an SN1 and E1 mix. And what I'm going to do is I'm going to put an asterisk here because OChem's full of exceptions. The blue asterisk, when can we observe SN1 or SN2 chemistry on primary or secondary electrophiles? Resonance can occur if carbocation is resonance stabilized What's another situation where these can occur? Yeah, some sort of rearrangement. I heard somebody say that in the back. So if you can rearrange into a more stable carbocation, these sometimes can be observed. Specifically, if you can rearrange into a tertiary carbocation or a resonance stabilized carbocation. So these can occur if carbocation is resonance stabilized or if it can rearrange into a more stable carbocation. All right. There's also another hint that I really like. So I'm going to put a, let's do a red star this time. We've got a novel way to really favor E1 over SN1. And we saw this in lab. How did we favor E1 in lab? Acid catalyst and heat, right? So secondary alcohols actually, let me do secondary or tertiary alcohols will undergo E1 in the presence of acid catalyst and heat. What's the acid we typically like to use again?
H3PO4.
Phosphoric.
Yeah, phosphoric or sulfuric. Those are the two you will most commonly see, and these really favor E1 over SN1. And this will occur on either tertiary or secondary alcohols. It's not super common with primary alcohols, though. It's a lot easier to do different chemistry that way. Does that make sense? All right, let's do a little bit of practice, and then I'll actually give you guys some time to work on your pod. And I really recommend working on these as groups, especially if you're struggling to conceptualize these. Talking it out with a friend or a partner is an excellent way of solidifying those problems. So let's take a look at an example, and then we'll jump into our pod. Okay, the first example is we've got sodium methoxide and we've got ethanol as our solvents. And we've got to determine what product or products we will get out. So I'll give you guys a minute to work on this, but try to talk it through with your partner. I'll give you guys a hint, too, to help you get started. If we look at sodium methoxide, is that a strong nucleophile, a strong base, or a combo?
Strong.
It's a combo, right? So this one would be a good nucleophile and base. And then what we'd want to do is look at the electrophile. So in this case, is it primary, secondary, or tertiary? Secondary. It's not sterically hindered, so now we can use that chart to our advantage or just try to use our gut intuition. All right, let's do another show of thumbs. A few more thumbs. All right, let's kind of reconvene and take a look at this. So we've got a good nucleophile, good base, and we've got a secondary substrate. So if we go up to our chart, say, oh, good base that's also a nucleophile, we've got a secondary substrate, that means we're dealing with something that's going to be E2 major and SN2 minor. That gives us a really good clue. So let's go back down and look at that, and we'll do both. So we know E2 is major, and SN2 is minor. On your pod, I'm asking you to circle any potential reaction pathway. So if there is more than one, circle both of them if they can occur. So let's do our E2 reactions first. And I'll say, you know what, I've got a bromine here. First thing we do with an E2 is we'd identify beta protons, and we'd say, hey, I've got a good base. This can come grab one of these beta protons, clamp down, and kick off our bromine, right? Oops, sorry, just one extra carbon. Let me clean this up. Is that the only product for this E2? What's our other product? Cis, right? So depending on that beta proton that we pick, we can get both cis and trans. Okay, are there any other E2 products we could get? Hoffman product, right? So we could say, hey, I've got some beta protons hanging off over here. Doesn't matter which of them I pull off. So I'll just grab one of them, clamp down, kick off the bromine. All right, so these are going to be our Zaitsev products. This will be our Hoffman product. Which of these three do you think is going to be the most major of our major products?
Trans-Zaitsev.
Yeah, the trans-Zaitsev. We know that the Zaitsev product for small bases is going to be favored, and we know that trans is more stable than cis. So this will be our major, and these will be our minor, and then this will be our minor. And then last but not least, let's do our SN2. Where we've got ethoxide, and this can do a sneaky backside attack, kick off our bromine. And is this correct? What's wrong? Inversion. A lot of people are still forgetting to do inversions with SN2 chemistry. Because it's SN2, we need to indicate that the stereocenter's changed by changing it to a dash. So in this case, this would also be our minor SN2 product. So the largest component we would get out of this reaction would definitely be this guy up here, our major Zaitsev product. Does that make sense? Yep.
So why did we do an SN2 if it was already minor and it was a polar protic solvent?
Yeah, so in this case it would be a very minor product. However, it's still something we might want to consider though, is if you're analyzing this, maybe 5% of it could be that SN2 product. It's not going to be a very big contributor, and if we did want to make it our greater contributor, we'd want to switch to a polar aprotic solvent. Yep?
Along the same lines, if we are in a polar protic solvent, wouldn't that prefer, if we're looking at a secondary carbon cation, would that prefer SN1?
That's a good question. So typically secondary carbons, unless they can rearrange into more stable ones, you won't see those because this is a really strong nucleophile. If we didn't have a strong nucleophile, then you could make that argument. Exactly.
Oh, okay.
If we didn't have a strong nucleophile, then you could maybe make that SN1 argument.
But doesn't SN1 not require the nucleophile be strong? That's
Exactly.
That's not a hindrance for it, right?
It's just that it's the only option. If you've got a strong nucleophile, it's much more likely to undergo SN2 than SN1. Any other questions? All right, so here's what we'll do with the rest of the lecture period. I really recommend getting started on the product with some partners next to you. So if you want to, you can push tables together and then start working through the pod, and I'll float around the room to help.
Are we allowed to circle more than